Hello viewers, in today's session we are going to discuss an important conceptual problem from integrals involving modulus function, and here we have to evaluate this integral that is from -1 to 0, and the integrand is the sum of three mod functions, that is mod of 1 minus x, then we have mod of x and mod of x minus 1, right? So now in order to evaluate this integral, we have to make use of the concept of definition of mod function, right? So here the definition of mod function is going to play an important role in evaluation of this integral, right? So let us first see the definition of mod function, and then we'll apply the definition to this integral, right? Although we can also solve this integral by taking the sum of three integrals, right? That is from -1 to 0 mod of 1 minus x, then from -1 to 0 mod of x, and then -1 to 0 mod of x minus 1, right? But here with the help of the definition of mod function, will simplify this entire expression in one go. So now a mod of p is defined as a positive p when p is greater than 0. So whenever p is greater than 0, that is p is positive, then mod of p is positive, right? And mod of p is 0 whenever p is equal to 0, and mod of p is negative p when p is less than 0, right? So let us apply this definition to these three functions. So here we have first mod of 1 minus x. So mod of 1 minus x is positive 1 minus x whenever 1 minus x is greater than 0, and mod of 1 minus x is 0 whenever 1 minus x is equal to 0, and this is negative of 1 minus x whenever 1 minus x is less than 0, right? So from here we can see that x is less than 1, from here x is equal to 1, and from here x is greater than 1, right? Okay, now a mod of x can be defined as positive x whenever x is greater than 0, mod of x is 0 whenever x is equal to 0, and this is negative x whenever x is less than 0. And similarly we can write mod of x minus 1, that is positive x minus 1 whenever x minus 1 is greater than 0, and this is 0 whenever x minus 1 is equal to 0, and negative of x minus 1 whenever x minus 1 is less than 0. So from here we can see that x is greater than 1, from here x is equal to 1, and from here x is less than 1. So this is how with the help of this definition we can define mod of 1 minus x, mod of x, and mod of x minus 1. So now let us call this integral as I, right? Now see here the limits of integration vary from -1 to 0. So here we have -1, here we have 0, right? So the limits of integration vary from -1 to 0. So a mod of 1 minus x is equal to a positive 1 minus x when x is less than 1, right? So whenever x is less than 1, then mod of 1 minus x is positive 1 minus x, and here all the values of x which lies in the interval -1 to 0 are less than 0. So obviously all the x are less than 1, right? So here we can replace mod of 1 minus x by positive 1 minus x, right? Okay, now here we have a mod of x, and mod of x is equal to negative x when x is less than 0. And here all the x which lies in the interval -1 to 0 are less than 0, right? So here we can replace mod of x by a negative x. So here we have negative x, and then we have mod of x minus 1, right? Now see here again x lies in the interval -1 to 0, and here mod of x minus 1 is negative of x minus 1 for all x which are less than 1. And since the limits of integration here all the values of x lies between -1 and 0, so obviously all the x are less than 1. So here mod of x minus 1 can be replaced by negative of x minus 1, right? So this is how we can simplify this integrand with the help of the definition of mod function, right? So in the first case, that is mod of 1 minus x, will make use of this part of the definition. Mod of 1 minus x is positive 1 minus x when x is less than 1. And in the second case, mod of x will make use of this part of the definition. Mod of x is equal to negative x when x is less than 0. So here x is less than 0. And in the third case, a mod of x minus 1, so we'll make use of this part of the definition, that is negative of x minus 1 when x is less than 1, right? So obviously all the x are less than 1 when x lies between -1 and 0. So let us now simplify this expression. So we have here 1 minus x, here we have negative x, and here we have minus x, and then we have plus 1, right? Okay, so now we can write -1 to 0, and here we have 1 plus 1 is 2, and here minus x, and minus x is minus 3x, and here we have dx. So now we can integrate this linear expression. So integral of 2 dx is simply 2x, and the integral 3x dx is simply 3x square over 2. And the limits of integration goes from -1 to 0. So first we'll substitute here x is equal to 0. So we have here 0, then here also we have 0, and then we have the negative sign, and then we'll take x is equal to -1. So we have here -2, and here we have -3 over 2, and -1 square, and -1 square is positive 1. So this is 0, and we have minus, and this is -2 minus 3 over 2, and this is plus 2, multiplying these two numbers by a negative sign. So we have here a plus 3 over 2. So this is 4 plus 3 over 2, that is 7 over 2. That is 3.5, right? So the value of this integral is equal to 7 over 2, or 3.5. Hello viewers, in today's session we are going to discuss an important and conceptual problem from definite integrals. And here we are given this problem where we have to make use of properties of definite integrals, right? So let us first read out this problem. And here we have the problem: consider a function f of x such that f of x plus f of 2 pi minus x is equal to pi square over 4 for all values of x belonging to the set of real numbers. Then we have to find out the value of this integral, that is 0 to 2 pi f of x sine square x dx. So now let us first take this integral as I. So here we'll assume I is equal to the integral 0 to 2 pi f of x sine square x and dx. Now let us make use of this property of definite integral, that is 0 to a, and we have say f of t dt is equal to 0 to a f of a minus t dt. So this is an important property of definite integrals which can be utilized in this integral, right? Because this property is a particular case of this one, that is a to b f of t dt is equal to a to b f of a plus b minus t and dt, right? So let us call this integral as integral number 1, and let us apply this property to this one. So here the value of a is 2 pi, right? And for f of t, here we have this function, that is f of x sine square x. So let us replace all these x by 2 pi minus x due to this property, right? So we have now I is equal to 0 to 2 pi, then we have f of 2 pi minus x, and then we have sine square, and here we have 2 pi minus x dx, right? Okay, now let us take some help from trigonometry. Now see, here we have sine 2 pi minus x, and from trigonometry we know that sine 2 pi minus x is given by minus sine x, so that the square of 2 sine square 2 pi minus x is given by minus sine x square, and that is positive sine square x. So here we can replace this term by sine square x. So we have now I is equal to 0 to 2 pi and f of 2 pi minus x, and here we have sine square x dx. So let us call this integral as integral 2. So now let us add 1 and 2. So adding 1 and 2 will get I plus I in the left hand side, and in the right hand side we have 0 to 2 pi f of x sine square x dx plus integral 0 to 2 pi, and here we have f of 2 pi minus x, and here we have sine square x dx. So I plus I is 2i, and here we can see that in both the integrals the limits of integration are same, right? And here we have sine square x, and here we have sine square x. So we can now write 0 to 2 pi, and we can take f of x plus f of 2 pi minus x, and then here we can take sine square x common, so we have sine square x dx. Now see, we are given in the problem that is f of x plus f of 2 pi minus x is equal to pi square over 4. So let us replace this quantity by pi square over 4. So we have 2i 0 to 2 pi, and here we have pi square over 4 and sine square x dx, right? So let us rearrange the terms. So here we have pi square, and here we have 4 times 2, that is 8, and then we have 0 to 2 pi and sine square x and dx. So now we have to evaluate this integral, right? So in order to evaluate this integral, let us make use of trigonometry, and we know that sine square x is given by 1 minus cos 2x over 2, right? So from the double angle formula for cosine function we have this result. So we have pi square over 8 0 to 2 pi, and here we have 1 minus cos 2x over 2, and here we have dx. So this is pi square. Taking this 2 outside the integral, we have 16, and 0 to 2 pi and 1 minus cos 2x and dx. So now we can easily integrate 1 minus cos 2x. So we have here pi square over 16, and the integral dx is x. So here we have x, and the integral of cos 2x is sine 2x divided by 2, and the limits are from 0 to 2 pi. So now let us substitute the limits, and we'll take the difference. So when x is 2 pi, we have 2 pi minus sine 4 pi. Here we take x is equal to 2 pi, and here we have 2, and then we have 0 minus sine 0 over 2. So this is pi square over 16. This is 2 pi. Sine 4 pi is 0. And here we have 0 minus 0, because sine 0 is 0, and sine 4 pi is also equal to 0, because we know sine n pi is equal to 0 for n any integer, right? Okay, so here we have pi square over 16, and here we are left with only 2 pi, right? So this is pi square times pi is pi cube, and here we have 8, right? So the value of this integral, that is I, is equal to pi cube over 8, which can also be written as pi over 2 whole cube. So viewers, this is how, by the application of the properties of definite integrals and some concepts from trigonometry, we can easily solve these kind of problems.